Cup, welcome to the 12th class of Big Data Analytics or Data Analytics, whether or not the data is big or small. I think I calculated, normally I think from previous classes, I would reserve maybe just one final lecture session for project presentation. But I guess that's based on group projects. So you could maybe like have 5 groups and then each group take about 20 minutes or half an hour and so forth. But now we have individual projects. So I think we have to squeeze things a little bit. It's a little bit tight, but what's going to happen is I think we need 2 periods, right? This is a final exam. So we have 2 periods for 40 students. I think that's doable. Okay, that's completely doable. So that means you should be able to present the project. Now, who's going to go first? Who's going to go on the 23rd? I guess we'll just randomize at some point. Okay. Again, what are the deliverables? We talked last time at some point, at some length about this paper with code idea. The idea that you have the paper and you also have the code that can be run. And again, this has 2 purposes from academic point of view. First of all, somebody else can verify that it's sort of independent verification that your code does exactly what you say it does on this set of data. And also, again, also for advancement of knowledge, for people to play with it and maybe use it in their work and maybe add some kind of enhancement or tweaking, right? And then share it back to the community. Okay, so that's a sort of output that is the baseline of any kind of data science exercise. Now, even though you might be doing this commercially, like I do for my consultancy clients, eventually you might do something like present a PowerPoint, but still, you can't really hand over a project which is PowerPoint. That's just not professional. Okay, so you have to have some kind of document, which normally takes a form of a project document, a white paper. And so this is also like a formal description of what it is that you did for the project, how you formulated the problem. So all this thing that we talk about in terms of the project, okay, problem, data, application, how you formulate the methodology, how you code, okay, maybe, yeah, all this would be described in that documentation. But for your class, again, and this is in line with the style of Basai students and program, you also have maybe like 2 or 3 minutes. Now, I did say 5 minutes presentation video. I apologize, but let's make it 3 minutes rather than 5. Okay, just make it 3 minutes. So it should be a very tightly scripted video presentation. Okay, so you should really actually have a script in front of you as you're making the video, and make sure that you can literally run everything within 3 minutes. Okay, 2 minutes would be even better. Okay, but let's say 2 to 3 minutes, but no more than 3 minutes. Okay, no more than 3 minutes. This is going to force you to allocate your time quite wisely. Okay, quite wisely. And let me open up the previous classes, class notes, side note. Okay, you still have to go through this, A, B, C, D. So the prologue, problem, solution, and a little bit. But again, this could be like maybe 1 sentence or 2 sentences if you did everything well, right? If you did everything well in the beginning. So this is kind of like a cut off 1 or 2 sentences. Maybe this is a little bit longer. This is about maybe a paragraph long. And then this thing is where, oops, sorry. This problem and solution is where you spend most of the video going over, okay? And again, that solution part covers, in theory, would be, in the paper would be both the methodology part and the results, okay? And the problem, you say, oh, what do you want to do and what kind of data you have? Okay, this is assuming we're talking about data science project. So you spend a lot of time on the data. If it's a paper about mathematics, maybe this is about talking about some kind of mathematical theorem, and there's no reference of data whatsoever. Okay, but for your project, definitely a big chunk of it is about what your data is. Last time I was rather happy to see what most of you did get going in terms of data preparation, data choice. I think 2 or 3 of you were using the same data set, and I think I convinced one to change. I'm not sure if you still have repeats. I still prefer that, you know, nobody repeats or uses the same data. Okay, right. And this should also make it interesting when you present. Okay, when you present, because your peers learn about it. Okay, so we talked about that last time. Now, today I'm going to go over, okay, again, the second part will be continuation of the project workshop with, I think, 10 or 12 views left, okay? So maybe we're doing pretty well in terms of time. So we can do like this in maybe 40 minutes or maybe an hour. Yeah. Now, what do I want to do first? I want to, part one, okay, this is something that originally I didn't have in the syllabus. It's more like, it's something that you pick up as you become professional data scientists. And there are, let's say, there are best practice of how to do certain things, okay? And you pick this up. But I think from the previous discussion, we talk about how important certain values are, certain variables are. This thing about testing, I thought maybe I should properly spend a good hour or two on it. Okay, so these are the like 3 things that I want to discuss. Data validation, okay, as a general concept, not just a particular technique. Sort of like the other thing is the pre and the post. Okay, so in machine learning class or in the previous lectures, we learned about how to build a model to do unsupervised clustering. We learned about how to build a model to do supervised learning, in particular regression, just estimating or predicting, forecasting some numerical values, or classification, with identifying whether it's a cat, a dog, or a good day or a bad day, good day, bad day, that sort of thing. Okay, so that's the bulk of the methodology of the result. But in professional work, rarely will you get something like a Kaggle. Okay, Kaggle is prepackaged. It tells you what's the data, okay, what is the training set, what's the validation set. All you have to do is just build a model, because the purpose of the Kaggle, I think, competition overall is not to compete on the overall data science method, but to compete just the middle portion, the model building, like who can build a better prediction model, better accuracy, okay, better differentiation, better discriminant, okay. So the platform, the Kaggle platform is sort of like giving you a little bit unrealistic expectation of your working life, because in your working life, chances are you're going to walk into a den of data or a data warehouse, and you have to sort of organize the whole data universe that you're working with and all that. All this is prepackaged for you. Okay, so when you go to Kaggle, same thing with when you go to Mathematica's data example, right? I think it was Mathematica use Mathematica data example or example data. example data. This is all pre-packaged for you. Okay. Now this is even packaged even nicer than Keiko, because this is meant for tutorial. So it's even more packaged. So you know that this is training set, this is input, this is output, blah blah blah. All you have to do is build a discriminant, a classifier, a clustering, all kind of thing that it asks to. And also importantly, once you do the analysis, once you build the model, how the model is used, in other words, to make prediction, how it's judged, precision versus recall, all this is almost defined, right? Because after all, Keiko is a competition, so they have to be a little bit transparent about how it's judged. So this bit about the post-analysis and pre-processing is not really that difficult. Okay. Now you may take the pre-packaged input and do more pre-processing, and that's your thing. Okay. You can do more post-learning analysis. You can do that as well. Okay. But in essence, if you work with pre-packaged data or curated data, you just focus on the middle chunk. Okay? You just focus on the middle chunk. Okay. So today it's going to give you a little bit of more complete pipeline. Okay. And it's more what you would do professionally. Now, when I say do professionally, I don't mean you as professional data scientists. You may be professional technologists. You may be professional biologists, but you have to do this data analysis professionally. Okay, so you're not a professional data scientist, but if you're going to use data science or machine learning or data analytics for your professional work. Okay, again, this class covers people who are going on to the sustainability and smart city and healthcare. Okay, not just hardcore digital intelligence. Okay, good. Now, so first thing, this thing is called, I'm going to cover data validation. First of all, we have to get to this concept. Okay, this first concept that you have to know is called accuracy versus precision. Okay, now if you go to, let's say, YouTube, I guess, if you go to YouTube, and then you go to accuracy, precision, right? In general, okay, yeah, maybe like 10Ed, something like that. Now, this is going to give you a very good understanding of what the two concepts are, okay? Accuracy just means that you're hitting where you want to hit, okay? So you aim right, okay? You don't aim left, you aim right in the middle. Precision, however, is because, even though you aim right in the middle, your shooting has certain variability, okay? So maybe I should enlarge this picture. I don't want this one to play. Okay, if you look at it, the bottom left-hand side is called accurate, meaning it centers around the target. So let's use this picture. We don't need to work maybe accuracy versus precision. Right. Look at some picture. Okay, let's look at some picture. There it is. Okay, let's look at this. This is a very basic concept that you should have this already, right? Okay. Now, what you like is this. What you like is this, okay? You're hitting the right target all the time, okay? Now, how can you miss? How can you miss? You can miss in two ways, okay? You can miss like this. You aim here, but sometimes you go high, sometimes you go low. That's called imprecision. So this is not precise. This is precise. But you can also be precise and precisely wrong, right? Like this. Now this is high precision. You're always hitting the same spot, but you're hitting the wrong spot. Okay? So you're hitting the wrong spot. So this is called precise but not accuracy. Okay? So this word is quite obvious. Now, Let me give you a segue. A segue, not a segue, yeah, a segue. There's actually one area where you will hear the word accuracy used incorrectly, but it is used incorrectly universally. In other words, 100% of the time. Okay, and that has to do with firearm. Okay, when you go to, I'm just picking up. This one I just searched this morning. This is like a firearm channel or something like that. Okay, I'm not gonna play it. Okay, but when this guy is talking about accuracy, what he means is precision. Okay. So what he means is actually precision. So when a gun manufacturer or a bullets manufacturer say it's very accurate, the quotation is something like minute of angle, meaning that if you try to hit a spot, okay, and you think of surrounding yourself with 360 degrees, you take 1 degree of space in front of you, you divide it into 60, that's called a minute of angle, right? If you're always hitting that spot, dum, 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 that's actually precision, okay? So it's minute of angle precision, but in firearm, they'll call that accuracy, okay? So that's wrong, that's completely wrong, but it's become standard vernacular American usage or English usage of the word. So this is where you will get the wrong idea of what it means by accuracy. So this is where they use the word accuracy, but they mean precision. So what is the problem? Okay. Now let me suppose you have two choices. Okay. Suppose two choices. You have two choices. You have between a high accuracy. Okay. You don't have this. Okay. You don't have this. This is perfect. This is terrible. It's awesome. It's everywhere. So you have a choice between accurate, aiming right, but all over the place. Okay, it's not precise. Accurate but not precise. Versus precise but not accurate. Okay, what would you prefer? Anybody? Not stop talking on the phone. Okay. So, what would you prefer? Accurate but not precise, or precise and not accurate?
The first one.
Well, it depends. If you cannot do anything, okay? You cannot change a single thing. You would prefer accurate but not precise. It's like shooting with a shotgun. At least you hit some, okay? So there's a 1 in 10, probability of shoot getting there. Let's say this is your target. So at least you're getting something right, okay? So most of the time you don't hit it, but 1 in 10 you hit it, okay? So yes, you're right, okay? Who was it? Okay, Sam or something? Yeah, okay. Yeah, if you cannot do a single thing, you prefer accurate over precision, okay? But if you are buying a gun, if you're buying a gun or buying a machine learning algorithm, okay, and you know how to measure your error, what you can do is literally recalibrate. So this would be like if you're shooting a gun, you move your side picture a little bit to the left, to the right, up and down, to correct. Then from missing 100% of the time, if you can recalibrate, you can move this thing over here. So out of the bat, you prefer accurate but not precise, because at least you're hitting some. But if you look at precise but not accurate, you're missing 100% of the time. But if you can recalibrate, again, this depends on your application. You have to know where your real target is, right? Now, if you know that you are off by this much, you would prefer to have precise but not accurate, because you can say, well, I'll just aim a little bit to the left and a little bit high, okay? And you shoot that, okay? So that's why, the firearm industry emphasize precision, but they use the wrong word, they use accuracy. Is that true in practice? Well, that's also not necessarily true in practice, because the only reason I can do this is because I'm shooting at a static target, like a paper target. So I can shoot 10 shots and measure the error, right? But imagine, what if in real life, I don't have a static target, I'm shooting a mouse. Every time I shoot, it goes away. You can never tell that you're actually 3 inches below and 4 inches to the right. You cannot recalibrate. So all this depends on how much you know about the real situation, whether or not you can calibrate, okay? But in a lot of cases, you kind of like this. But in machine learning, okay, I think it's the opposite of the firearm industry. The firearm industry, they always say this, adjust the sight, which is rather silly because you can do that with paper target. You can't do that with a real mouse, right? So with data science, goes back to the first answer that you gave me. Chances are, yeah, you prefer something like this. Chances are, okay, but not always. So you have to realize that, yeah, there are 2 different criteria. Now, if you think about it, they don't have to be mutually exclusive, but you can think of it as a good quality model would have both. A bad quality model or an average quality model can be poor with respect to accuracy or with respect to precision, or both. Okay, so with that out of the way, okay, you have to realize that this is really the trade-off. You can imagine the trade-off between precision and accuracy would be something like buying a cheap ammo or cheap gun. Okay, you can only choose one that has the sight set correctly, but the bullet groups is all over the place, or one that has a very precise bullet group, but the sight picture is off. Okay, let's say you must choose between those. Okay, but if you have more money, you can buy a gun or bullets, a set of bullets that are good in terms of both accuracy and precision. Okay, so with more money. Okay, so the trade-off is not necessarily static either. It's static, given maybe a budget. Likewise with neural network. Okay, we'll get to that. But let's go to the second concept. Well, let's turn this thing from accuracy and precision to bias and variance. Okay, now this is where you turn a concept, again, that's very general, applies to shooting bullets, to something more statistically grounded. In other words, bias is the statistical equivalent or statistical concept of accuracy. In other words, it's difference in true versus model mean. Okay, it's the difference between true versus model mean. So mean is the statistical. Now you have statistical concept, right? So whereas the variance is the variability of the model output, right? Model Y. Okay, so true Y versus model mean Y. That's it. That's a variance. But this is not the end of the story. Okay, because when you go to machine learning, it's a little bit trickier. What do you mean by variability? Okay, so I'm gonna erase this. And I'm just going to say, well, yeah, now, yeah, bias is about mean, okay? That's the wrong mean versus variance, okay? Variance or square of standard deviation. So now it's more statistical, right? So this is a general concept. And this is more statistically interpreted. Yeah. Now, the next concept is what I just alluded to just now of the trade-off. Now, this is not always true. Okay, it's not it's not a given. It's not like you have limited budget, so you have to buy a cheap gun, so you have to get either one that's one or the other. Well, this is actually not always true, but in life, yes. In data scientist life is yes. And what's sad? Okay, here's what's sad. Here's what's sad. What is sad is that with buying handgun, you can buy more expensive handgun that is more precise and more accurate. If you spend more, okay? If you spend more money, you can do that. Whereas with data, this is a feature of reality. In other words, you cannot build more complicated model. You cannot build a better model and get rid of everything. You up to a point. So there's a balance trade-off, because up to a point, reality is somewhat random. Okay? So you will miss. You will miss in terms of variance, or you'll miss in terms of bias. At some point, you cannot buy your way out of the solution. Okay? Because sad. Because up to a point, reality is somewhat random. Okay? Partly. So that is a variance and bias trade-off. Okay? So you get a so this is still the same concept. Now the next concept is variance bias trade-off in machine learning. Now this is different. Okay? So now you move away from statistical concept. Okay. Now, this is where I refer you to this video, which you can watch at your leisure. But I'm just gonna skip the ad and go to the pictures. Okay. I'm just gonna say, let's go to, let's see, where are we? Let's go to somewhere around here. Okay. Do you guys remember? The example machine learning that I show you about this female height and weight? You guys remember this one, right? You guys remember that, right? And so we built a model and make a prediction. Okay, so this should take 2 seconds. Hold on, where are we? Okay, that's height and weight, female height and weight. And that's my model data. That's built a model. And okay. You remember this? The model is very accurate, right? Okay, but keep this picture in mind. The little error you see has a pattern in it. Okay, so it's a little bit underfit here, and overfit in the middle. So there's a pattern to it. There's a pattern to it, right? There's a pattern to it. Now, let's go to this picture. Where's the internet picture? Okay, the same thing here. It's exact same picture here, except this picture is exaggerated. Okay. Now it turns out that because of this data set, the straight line is not good. So you have to go with a curved line. Okay. So straight line is not good. You have to go with a curved line. But then you say, well, if you can curve, why not go all the way to this? Okay. You can fit all the point. Okay. So here's where you change the meaning of the word bias, right? It used to be bias means wrong mean. Okay, now it still also means wrong mean, but this is kind of like more nebulous. Might mean not the best. Okay, now this is, again, data scientists don't have better definition yet, okay, but bias means it's not the best. What do I mean by not the best? Straight line is not the best. Squiggly line is not the best. The best line is this curved line. Why? Because not the best in the sense that, in the sense of capturing true nature of the function x. Yeah. Now, all of this I can make up. I don't need this anymore. Okay, all of this I can make up. Why? Because I'm generating the data. Okay, what I did, what this guy did was he generated this curve deterministically. Y is equal to, say, log of x. And then he adds random noise. Okay, so if y is equal to noise, yeah, if y is equal to deterministic function with noise, then if nature gives you this, if nature gives operates according to this, okay, then the best model is f of x. Yeah. Anything else that explains noise, no good. Anything else that doesn't explain this, also no good. So you have two things, all right? Bias means not getting fx right. Not getting fx right. Variance means getting noise. Okay, means you're actually fitting noise. Okay, so make you can do this mental simulation in your head. Say nature, okay? Nature has two things. It has deterministic function, y is equal to f of x, and it has noise. Okay, so think of f of x as physics. Noise would be something else. It's also physics, but you can't take into account, like some wind or something like that. So this is shooting projectile, and this is some kind of error from the air. Okay, what you want to do is get f of x. You can fail in two ways. One way is you don't get all the f of x. That is bias. Okay, so that is equivalent to statistic not getting the right means. But variance means you're actually fitting the noise. Why is it called variance? It's called variance because it means variability of model performance when you get another data set. Of noise. Okay? So that is why it's called bias and variance in machine learning. Bias and variance in machine learning is not a statistical concept in the way that this thing corresponds to means and this one corresponds to square standard deviation. Okay, so be very careful. Be very careful. Last year, if you study statistics properly, you will know about bias versus variance. That will have statistical meaning. Bias means you don't get the right mean. Variance means the standard deviation of your model is all over the place. But in machine learning, they adopt this term, okay? And I really don't like this at all. To be honest with you, when I was a student, throughout my PhD year, never once did I use the word bias and variance trade-off in machine learning, not once. This only became common usage in the last 10 or 20 years. And I disagree with it strongly, but you have to realize that this is how they mean, okay? It's not bias, it's not. It actually means you are actually not getting the right model. So it's basically the poor model, okay? Variance means you're fitting too much. So in other words, let me give you an example here. Okay, if you think about it, and let's go back to our example. When we fit linear regression to a nonlinear function, okay, when we fit linear regression to a nonlinear function, and that's the example we did here. This is a perfect example of bias in machine learning. Okay, now this doesn't have in sample, out sample yet. I'm gonna go over that, but this is exactly the concept. The concept means you're not hitting the right function. You're not using the right function. You're not using the right linear kernel. I think somebody was asking about using SPSS for linear regression, and I was saying that linear regression, yes, use SPSS, but if you want to use nonlinear kernel, you're still better off with Mathematica. So in this case, if you build a nonlinear kernel, you will get a better model. So this is a poor model. It's a bias, right? Fortunately, the element, the misfit is so tiny. So that's like when you're fitting linear regression to a nonlinear function. This is what the bias is. Over here. It's like, yeah. On the other hand, variance means you get overly complicated model that did exactly this. Okay, if you go home and play this video, the narrator may say this is from a complicated neural network. It's literally gonna memorize data point. Okay, what happened is when you get to the data set that doesn't have this other set, you used to get perfect fit, now you get terrible fit. It's that variability that they talk about when they say variance. Okay, it's that variance. Okay, it's that variance. So now you understand that you know, with bias, variance trade-off, this is a very important word. Bias variance in machine learning, conceptually similar but different from statistical concept. Okay, so actually, what I would like to do is, if I were able all powerful, I can tell YouTube to delete all the videos that have to do with bias and variance trade-off in machine learning and just remove all this together, but I can't. Okay, so I have to tell you here. But the better concept is called fitting versus generalization. Fitting means you're trying to fit a data. You're trying to fit the data to the best possible ability, in which case, this is a perfect fit. But this is a poor generalization, because when you get some new data set that the model hasn't seen before, it didn't memorize, it only memorized the blue, it didn't memorize the green. And this is where it makes more sense to think about data partition. Data partition. Okay. Partition. So maybe I should put the word here. Partition. Okay. So now you partition two things. You partition in sample versus out sample. Now, when I was young, it was called out of sample. Okay, but nowadays people just shorten it to out sample. Fine. Okay. but it used to be called out of sample data. What it means is that you have, say, 1,000 X and Y pair. Okay, you partition, say, 900 pair as in sample, and then then keep in a safe 100 pair as out. Okay. Okay. You build model using in sample data, but then you test model using out. Okay. So this thing is gonna be very good at fitting. This means, is it also good at generalization? Okay. This is something you actively do, and this is where the gradient descent, all the machine, this is where all the machine learning algorithms are designed to do. Okay. When we talk about machine learning algorithm, it's about learning from the data. It's learning to fit the data. Okay, it's learning to fit the data. And if you give the computer, you give the robot a task, it's going to do the best it can. So it's going to fit the data the best it can. However, it may overfit, in which case is it good at generalization? It's the same thing as asking, did it overfit? Over. Okay. Did it do this? If it did this, it overfit. So how's it gonna tell you? It's gonna tell you because you feed the blue, this is an example to train the model, you get 0 error, 0 error. The model is perfect. You test it on the green, green is your out of sample, and you get terrible result. It's actually worse than linear regression. If you think about it, linear regression would actually do better, right? Because some data is up and down, kind of averages out, so you get this kind of linear line. So if you get some kind of rough guess in the middle, you're probably not so bad, right? Whereas here, you actually off, when you write, you get 100%. So if you think about fitting a straight line, it's gonna have some error. Maybe it has 10% error here. It has 12% error here. But an overfitting model will have 0 error here and 25% error. It's the variability in error with respect to data set. So I go back to say that variance technically is variability of model error with respect to different data set, different sets of data. Technically, this is what it means. Technically, okay. So now the definition is complete. Now definition of complete. So this is called fitting versus generalization. Now, this here is what's called so I'm going to draw this picture. I'm going to draw this picture. Now, imagine that this is my error function. Okay. This is my error. Oops, sorry. Okay. This is my error. So if this is my error, I want it to be error. Sorry. Of Okay, this is my error. Okay, and this here is sort of like training. Okay, you recall that lecture a while back when I talked about this this machine learning as linear regression as a machine learning. Remember this, right? Right. So what happened is you got some original error here, and you want to keep going down, 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 down. Now, if you don't look at the error terrain, you take just the amount, just the level, just the amount here. Okay. As the model gets better, it should go down. Okay, it should go down. It should go down. It may, you know, have a little randomness here. It may be squiggly, but roughly speaking, it goes down. Okay. So in reality, it kind of looks like this. Okay. But I'm just going to idealize it. It kind of looks like this. Okay. So the error is going to go down. So that would be like trying to fit the blue line. Eventually, it's going to get to the point where it almost near zero. That's why it took near zero. Okay, goes all the way down to near zero. But at every point now, every point is a single model, right? So I draw it as a straight line, but it's actually a point at a different stage of the model. Okay, if I use that model and I test it against this green data, so this is basically performance against the blue, it's going to look something like this. So it's going to get better, but at some point it's going to be worse. Okay. In other words, it starts from not fitting anything. It's going to get better fit, better fit, better fit, better fit. But at some point, it's going to overfit. Okay, it's going to be overfit. Now, obviously, right? What is the best model? It's not all the way here because it overfit. So where is the perfect fit? The perfect fit is right here. So what you do is you train a neural network with respect to this training set, but you test it against this second set, right? The second set. And whenever this one starts to get worse, you stop. This is called early stopping. So you can do that. Why can't you do this in practice? Why can't you do this in practice? Why can't you use this for the blue and this for the green? So, okay. So what you want to do, wish to stop neural network when out sample error goes up. This is what you wish to do. Why can't you do it in practice? Anybody? It's a sheep. Because by nature of out sample, you can't use it to influence your model. Right? You're using your blue data to train the model. But you're also using the green data to stop. So you are using both of them. That's illegal. That's not a real testing, right? Think of testing. Testing is like if you have a training, like I'm teaching you right now. When I test you in an exam, I have to give you something else you've never seen, right? Right? What if I give you an exam right now, so you can say, okay, focus on this chapter. Don't stop learning about this chapter because you're learning too much or something like that. So it's like a hint. The green one is used to give a hint and say, aha, don't go all the way down here. Stop here. It's best. Quit while you're ahead. That sort of thing. Okay. So this is completely illegal. But that's what you want to do, correct? If this is what you want to do, but it's illegal, this is how they get around it. Instead of making this in sample and out sample, you separate the in sample into validation set. So, cannot do because it would be cheating, i.e. using out sample to help guide model building. So how to get around it? To get around, you leave out of sample alone. And take in sample, okay, and then partition into two parts: training and validation. Okay. So now, instead of here, let's say I have here 90% split, right? So now you take from 90-10 split to 90-10, and then you separate this into something, let's say 70-20, okay, right? So instead of training, so from in sample out sample, okay, to training, validation, testing. Okay, and you can put another bracket here just to emphasize. This is what I do. Okay, and people would do. Okay, now there are two cases in real life. Okay, remember this model? It cannot overfit. Can it overfit? It cannot, because it's a linear model. It's incapable of overfitting. So what happened is that you would use 90 to train machine learning that cannot overfit, e.g. logistic, regression, or something like that, okay? Which is linear, okay? And then you would use 70% to train ML that does overfit. That's 10 to it. Use 20%, okay, to stop ML from overfit. Okay, so there are two cases. For a model that is simplistic, again, so logistic regression, maybe you can put support vector machine, or, you know, something like that in here, okay? Now, where are we in 2020? Especially what? Deep learning, right? Because deep learning has so many parameters, you can memorize the whole picture. Okay. Now, this 70-20-10, this is, you know, you can make this 15 and this 15. This is just an example, okay? In fact, so that's not really the essence, okay? Okay. Right. So this is where you separate, okay? And this is, so now you can say something like training versus validation versus testing. So in your project, if you're using, say, logistic regression or support vector machine or something like that, you can split, you know, 90-10 or 80-20, okay? Whereas with this, you have set. Okay? Set. Okay? So instead of having in sample set versus out sample, you have training. Okay, so let me put, so that's it. So in your project, okay, now let me just mention some special cases. What about things like decision tree? Right, we have picture of decision tree, right? Remember that? Well, if in decision tree, I could say here, decision tree with limited branching. Whereas in some algorithm, if you use Python or something, okay, you use a decision tree with unlimited branching. If you have unlimited branching, you can actually go all the way to every single data point. Literally. That's why it's called memorizing, right? Okay. So it's unlimited branching, for example. Deep learning, multi-layer perceptron, all kind of stuff. So chances are you will be working with this. Okay. Okay. So this is what your project would, well, depends on what you use. Okay. Depends on what you use. Now, there's another concept called K4 validation. K4 validation. This validation doesn't refer to this validation. This validation is a whole loop outside of this. In other words, it's something like this. Okay, something like this. It's A into partition A into A1 and A2. Okay, so you can do this. You can do this, right? Into something like 90% and 10%. The point is that K4 means you can choose K different location of the 10. Yeah. In other words, okay. In other words, if I have, I'm just going to draw this thing. Okay, let's say random variance uniform. Okay. Okay. Now notice, if I'm going to take this as my training and this as my testing, I'll get some value. Now, if I do this 10 times, instead of take the first 90% and then test on the last 10%, I take the first 80% and the last 10% and then test on the second to last. I get another number. If I take the first 70%, and combine it with the last 20% and test on this, I also get another number, right? How many times can I do this? I can do this 10 times. Okay, so a 10-fold validation would be, using different blocks of 10%. A 5-fold validation would be something like using different blocks of 20%. Okay, 8-fold validation would be 8 different blocking of 12.5%. Okay, so I take the last 12.5 data and then so forth, right? Now, this can be done in a structured way. In other words, you line up the data and you just get this index, or you can do some kind of random partition, depends on different algorithm. Okay, but this K-fold validation applies at this top level. Generally applies to the in-sample out-sample split. Okay. Okay. And this is more of a quality assurance that you're not just lucky. Okay, so it may be that you train a model on 90% and you test on the 10%. It happens for that 10% to be so easy to predict or something like that. Okay, so you do this 10 times and then you average the result. Okay. Now, you can also do this K-fold thing between training and validation. You can do that as well. Okay, and people do that for a very strenuous analysis. Okay, but at the very minimum, K-fold validation, it's not a split between training and validation, but it's splitting between in-sample versus out-sample, generally. Okay. Scheme to split training. Okay. No. So that's it. That's all the comment I'm going to make. So this is the whole sort of making sure that you're not overfitting. Okay, this is a whole thing called making sure you're not overfitting, and this is very important. Now, it's very important where is it important? It's gonna important in the post-analysis when you report the performance. So this is why when I build a model, okay, I will have something like a model training data. Yeah, and then I have a testing data, and then I have something like my model. Okay, is equal to predictor, and then training data. Okay? Now, I haven't defined any of this, so never mind. Okay? And then I say my model performance equal to predictor measurement of my model. Now I can put two things. I can put in sample or training data, right? So I would say testing data. Yeah. So this would be something like training data is the same thing as in sample. Yeah. So this would be like a decision tree. Now, if so method go to linear regression, yeah, something like that. Okay. Now, whereas if I have a method, the neural network, I'll put training and validation data. Okay. So basically, this is what you want to do. Now, I'm going to skip. I'm going to skip number 2 discussion on pre-processing. I'm going to go ahead and talk about post-analysis. Why? Because post-analysis basically has, let's say, has 2 points, has 2 parts. And the first part is very much related to this in-sample, out-sample split. Okay, so I'm going to shift gear, and I'll come back to this. So I'm going to cover 1, 3, 2, and then go to part 2, which is the student project. Okay, but I still have 1, 2, 3 because this is post, so it should come after pre. Right. So post analysis means what? Think of your project. Okay, you build some kind of project, some kind of model. Okay, build it and whatever. Okay, here. Okay, so you build some kind of model, right? Some kind of model. What are you delivering to your user, to your client? There are two things. There is a primary deliverable and there's a secondary deliverable. But I use the word carefully because sometimes secondary deliverable is more useful. Okay, but it's a secondary deliverable because it comes after. So the first primary deliverable is the model, right? So think about it. Yeah. So what you want to do, you deliver two things. Primary deliverable model. As prediction or whatever. Okay. Oops. What's the secondary? Well, secondary deliverable is insight about the okay. So, for example, I'll give an example. Okay, I'll give an example of a primary versus secondary deliverable. Now, this is a universal term, I guess. So maybe I better put that in. Okay. So, for example, model that predicts whether a person will buy your product. Okay, so that's a model, right? So X is the characteristic person. Y of X is equal to either Boolean, true or false. Right? Okay, likely or not likely. Okay, right? So that's it. Your job is done. As a data scientist, you get paid to build a model that predicts whether or not the person will buy a product. That's it. You're done. You're finished. That's your primary deliverable. That's good. Okay. So, what you want to do? You want to make sure that this is good. So you have to assure quality of your model, and this is where you talk about model performance, right? So this is this bit here, this classifier measurement. Yeah. That's how you assure the quality, right? You do all this. You say, oh yeah, you get the diagonal right, you have the right recall and precision and so forth. That's what you want to do. Okay. So that's it, you're done. But this is a secondary deliverables. Maybe I should put S. For example, the secondary deliverable would be something like, it turns out that, say, sex is the best determinant for product A, but salary is the best determinant for product B. Okay. Something like that. Okay. So maybe you don't build just A model, you build B model, right? And it turns out that, wait a minute, you're getting the prediction. Let's say you get the prediction, but you don't care just about prediction. You want to look at the results. Yeah, this person gets predicted. It turns out actually A, for product A, sex matters the most. Okay, so obvious answer would be something like skirts or something like that, right? If the person is female, she's more likely to buy skirts than male or something like that. Now, whereas something like B is a luxury product, so maybe salary. So that would be too simple, right? If you can do this, you don't need a data scientist. Okay, but that's the sort of thing. That's the level of information. So notice, this is what the model does. This is what you build a model. It does what it promises. Well, so you have to assure that, yeah, it's got good quality. Yeah, it does this, it does this. But you can also deliver this thing called, well, it's sort of like derived insights, additional insight, device or additional or quality assurance or, you know. Yeah. So if you think, so the first concept is this. Then let me put this away. Yeah. So the performance, again, we talked about this at length. For regression, basically you go to predictor measurement, right? You go to this page. So you go to this page. Because you are actually doing regression, right? Your output is like values, right? So basically you look at the residual. The focus here is on the residual, okay? You can say predicted versus actual, what the difference is residual. Now, let me just make a small note. You want two things. You want the residual to be small, okay? Which in this example, yeah, good, it is small. Residual is small. But you also want the residual to be featureless. In this case, this one fails. As simple as this problem is predicting female height from female weight, this model is highly flawed for this second criteria. Yes, the error is tiny, but there's a feature to it. There's a pattern to it. It's high here, it's low here. In fact, if you take this 45-degree line and turn it up here, you will see a problem. Okay, so what you don't want is to have some kind of feature. So you want it to be like featureless, what's called white noise. Sometimes they call it white noise or featureless or normally distributed. Okay, so basically completely noisy. Okay, there's no pattern to it. Okay, that's what you want. Whereas regression, well, regression we talk at length, talk about true precision. We want to talk about precision and recall, right? Precision, and this is another word for precision. Has nothing to do with the word precision over here, right? Okay, so it's really funny. Okay, so when you talk about firearm, they talk about accuracy. So they talk about precision, but they use the word accuracy. They don't use the word precision. Here, they use the word precision, but they don't mean that. So they have a different meaning. In this case, precision just means that, you know, did you make the right call? Okay, precision, where's precision? Precision, 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 precision. There. So of all the positive case, of all the cancer that you diagnosed, how many were really actually cancer? Did you make the right call when you did? Okay, of all the calls you made, all the prediction positive case. Whereas recall would be of all the real case, did you catch them all or did you catch most of them? Okay, so true positive versus false negative. So basically, those who are really positive, of all the positive, did you get them? Okay, so those are the criteria. Okay, now I want to focus. So this essentially here, this is why I'm talking about this thing number 3 instead of number 2, because this here is not invariably, these are taken against out sample. Okay. Now, some people would report in sample performance as well, but you really can't deliver and promise on this. Okay, so really it's the testing. Now, occasionally there would be 2 testing, or historical versus live. Okay? In other words, when you take all the data in the past and you take 10% out, that's historical. Okay. Now, once you deliver the model to your client and the client is using it, now the day starts, the clock starts. You get completely new. This is the future now. This is the live model. Sometimes they would do this and then measure this and see how well your model did. So this is really out sample, way out sample. Okay, this is out of horizon. This is the future. So real data, real future. Acid. Yeah. So you can't do K4 validation in this. Okay. So with historical, you can do K4, right? Because you can decide, okay, I'm just going to keep the last 10% as testing, or I'm going to keep the second to last as a 10% as a testing. You can do that. But if your testing is live, it's future, it's the next month worth of sales data, you can't do K4. Okay. Yeah. So that's just a little, it's a little bit obvious actually. Okay. Now, let's focus on this. Performance criteria. Okay. The performance criteria here really is to help with the quality assurance. That it's doing the job it's supposed to do. But hey, what about second criteria? Okay. And this is where we're talking about, and let me add a little segue here. Okay. I don't know if many of you have seen this, and you see this kind of discussion between the black box and white box, and say neural network, black box. I don't know, we should trust them, something like that. Okay, it's a little bit, it's one of those AI scare kind of thing. This is rather silly. First of all, because black box is really not black. It's only black to people who don't understand how it works, right? If you think about it, a black box it's not a black box at all, because somebody has to create it. I created it. I'm a data scientist. I built the damn thing, so I obviously know how it works, right? So you should say that it should not be a black box. Well, it's a black box if people who build the model just take in some kind of library like Mathematica or Python and just build it and have no idea how it works, and never test it, never experiment with the data, don't study the data, have no mathematical understanding. Yeah, then it is a black box to the builder, right? But that should happen. To a professional data scientist, it shouldn't look black, because even though you don't code the thing yourself, you use software, or you use free codes from GitHub, you still know how it works in principle. So it's not a black box, right? It's like an engine, okay? Some of you may actually have no idea how internal combustion engine works. because all you do is sit in a car and you can drive it. You don't know how the engine works. But some of you, from might want to modify your car to make it go faster, and so you modify the engine mapping. So you know how it works. You know how the engine mapping works. So it's not a black box to you. So this is rather silly. So let me just mention that. Okay. Now let's go to out. Now, what are additional insights? Okay. Now this already, I gave you an example of the additional insight, right? Turns out that sex is important for product A, but salary is important for product C, while both are important for C, for predicting demand. Okay. Yeah, something like that. Okay. And so on. Right. So what kind of insights do you think that people want? It's going to be like this. It's going to be similar to how it works. But how it works, if you think about it, let's go back to that engine again. Okay. Let's say you want a car that gets you fast from here to there. Okay. That's like primary deliverable, right? So you get a car. But the derived insights, okay, the basic fundamental theory is how the neural network works, how the engine works. But usually, secondary deliverable is sort of like, how can you tweak it? Okay, what are the variables that really matters? So you understand now, you know how the engine works, but really what you like is how can make the car go faster. You understand the principle of internal combustion engine. But really what you're after is tweaking, is kind of insight. Actually, you know what? The car will go faster if it breathes in more air, or if it can expel exhaust without restriction. Okay, so I'm gonna put different exhaust that doesn't have back pressure, whatever. Okay. What is gonna make the car maybe not go so fast, but have high torque, because I'm driving a truck and I want to haul my yacht, my boat, my whatever, that I'm hitching my motor car up a hill, okay? So then I can choose the kind of car that produces a lot of torque. Maybe I'm designing a car, I'm designing the engine, whatever, modifying, all sort of stuff. Okay? So it's not just how it works, but what affects the outcome. So it's not give me X. So I want to predict Y. Given I give you X, you predict me Y. No, okay. It's a little bit more like, well, if I really like a lot of Y, what kind of X would I like? Okay. So if you think about it, you kind of like to do inverse problem. Okay. So let's think of insight. Okay. Yes. Now you have a very good model for predicting Y as a function of X. Now you want to tweak, i.e. get more or less Y. Okay? Ultimately, this is, if you know everything, basically what you want to do is this. Y X is equal to F inverse. If you do this, by the way, and this is a general concept, this is sort of like godlike knowledge, right? If you do this, you can do things like optimization. Choose X to get the maximum Y. Right? You can do that. If you knew you can do things like optimization. Okay? But in life, in practice, F inverse is not available. Okay? So, what's the next best thing? Next best thing, how would y varies if I vary x? Okay, so this is a different question, right? Okay, first of all, the tool you have is give me x, predict y. And if you have a godlike knowledge of how the world works, you can flip this around and say, I can choose my y from x. Normally you can't do that. But what you can do is you can twiddle. You can twiddle. Change the x a little bit to get a little different y. How can I do that? It's this kind of insight that you want to have. You want to know, so in a more general sense, in essence, how does f depends, or how does f work with x? Now remember, x is a vector. So you mean 1 x n. Okay? You don't mean a single x, right? So this is where explanation or feature importance comes in. Okay? So once again, you have a vector x. Of the hundreds of x's of xi, how does whatever x7 contribute to determining y? Okay, so this is sort of thing you want to ask. This is sort of thing you want to ask. Yeah? You can ask something else. Overall, does x7 matters more or less than x? Well, okay. Whatever. So this is a sort of thing you want to do. Okay, ultimately you want to ask things called feature importance. Feature importance. Okay, and this is where it gets to a very, very powerful tool called Shapley. Okay, so you see this question here, right? So basically you have bunches of x's. You want to know how does individual x affects the outcome, and does it really matter, right? It's like I'm looking at a class of 2021 and see if some of you, are contributing to class discussion or whatever, right? And some of you are more important than the other or something like that. So it's sort of like if you have a group contribution, right? The whole thing, y is a function of x1 all the way to x100. I want to know how important is x7. Okay, so that's really how to, the word is, the general thinking is how to determine individual contribution from aggregate group influence, right? Now I put a little segue here. I'm not going to talk about it. If you're interested in finance, there's this thing called marginal value at risk, where you, if you have investment in 100 asset, and the value at risk is like a measure of your risk. sort of like loss or something like that. And you want to say, well, how much of it depends on this particular stock that I just bought this morning? So you can compare maybe calculation of value at risk with or without, okay? So you can do something like VAR with all the stock versus VAR with all the stocks except this one. Okay, you can do that. You can do that. So that means you have to do 2 calculations, right? You have to do 2 calculations. Well, let's just say, let's just ask you in general, how would you do that? Well, if the process is straightforward, you can do this. You say y is equal to f of x1 x100 versus x6 x8. You write it there, right? So the full model, so this has 100 variable, this one has 99 variable. Okay, you can do that, right? Fine. So I can say, you know, what does it do? So if I calculate this, and let's say this average of y is 100, this average of y is 200. So that means having x7 push the value up, doubles the values, right? You can do that. Why wouldn't you do it? Well, think about it. You have 100. If I want to measure relative importance of x1, I have to do this, what, how many times? 100 times. It's basically impossible, right? So this, you know, in finance, you can do that because you can calculate fairly quickly in some case. So can you do that? Short of doing this, what can we do to gauge importance of y x7? Okay, so input. So instead of 6 and skip to, I'm going to say x to the I minus 1 and x to the I plus 1 for all. Short of doing this, that's too much. So what can you do? Well, some clever people look back at other clever people. This is called game theory. Game theory is a very elegant mathematical construct. Okay, Lloyd Shapley, I think he's still alive. He came up with this concept, Shapley. Okay, so the concept, he came up with it. He probably didn't name it after himself, but once he published the concept, people honor him. So they want to calculate the Shapley value. Shapley or Shapley, I don't know. Let's say Shapley. Okay, it's named after this guy. Okay. In this case, it's not contribution to the model output, but it's contribution to what's called cooperative game. It's like a good example, and they always use this in this discussion. It's like if you have groups of 5 people sharing a cab, okay, and the cab drops all 5 of you at different addresses, and it costs the whole trip 200 baht. Okay, how can you split that? Okay, 5 friends, 40 baht each. But wait a minute, the first friend only lives 1 block. The other friends like live way out in the countryside. So it should be a different kind of averaging. So the idea is that if you have some kind of messy, okay, so this is kind of messy entangled contribution. You can't really say, you can't say something like contribution overall equal to sum of individual contribution, right? So in this case, if the individual contribution is amount of cap fare, you can just take that individual contribution, divide by total contribution, right? Then you're done. You can just take individual contribution, divide by total, okay? If this were the case, life is simple. But it overall, it's kind of entangled mess, combinations of, you know, all kind of weird combination. How would you break that down? How would you break that down? So that comes in game theory. This is called Shapley value. So Shapley value is a way of estimating individual contribution to the whole group, team effort. Okay, it would be like something like, you know. So this would be something that is the game theory. Likewise, let's look at our problem. Let's look at our problem. Let's say y is a function of 4 variables. Again, the first derivative is done. You build this model, it's good. It's good model. Y is equal to f of x1 to x4. It's good. Now you want to know insights. Does this model really care so much about x1, x2, x3? Because after all, x1, x2, x3, x4 may have different costs of gathering, right? Some data field is easy to take the value of. Some of them require, you know, a more extensive data gathering, more expensive harvesting process. Okay, so I want to look. I say, okay, now, okay, it's a good model. Okay. Given a good model. Okay. What accounts for specific contribution of this one? Now, let's look at a single data point. Okay, let's look at single data point. In other words, okay, in other words, I want to know that, so star is like a single point, okay? And I want to look at influence of x1. So how does x1 influence this value? So obviously you have to compare it with other values, right? So let's say consider the two extreme example. Okay, one. Okay, one approach is I don't care. I think x1 is the most important thing in the world. So it doesn't really matter what x2, x3, x4 is. So basically, I can just take an average of the value of this point and the other point, right? So this is the value of this point. This is the value of other point, and just take a random sample. Maybe take all the data, okay? When I say sample, I can mean the whole data if you have all the time, but you can just say average of some sample, okay? Is that smart? No, that's obviously not very smart. That's not very smart. Because why is it not smart? Because actually you're not measuring the effect of x1. You're measuring the effect of everybody, right? Because everybody changes. That's stupid. That's not smart. That's a bad way of estimating impact on x1. What is another smarter way of estimating the impact of x1? And this is the method that economists use. Okay, it's called all else being equal. Okay, and pronounce this properly. Let's go to internet for that. How to pronounce okay. Wait a minute.
Ceteris
paribus. Yep. Okay. Ceteris paribus. Okay. And that's what economists like to say. All else being equal. So what you do is, for this point, okay, how about substituting in, right? Substituting in other Sorry, I wrote this down wrong. Right? So if I vary this, I care about x1, right? So I vary the value of x1. Okay, that's all else being equal. Now, this looks smart, but actually this is also dumb. And economists are also dumb for this reason. You can do this for a very tiny movement of x. Okay, this is called partial derivative. Based on partial derivatives. And economists does this all the time. Economists, okay, this is my segue, my segue. Economists does this, okay? Economy is a function of A, B, C, D, E, F, G, okay? And to measure the effect of E, they just vary, but you can only do it just a tiny bit. If you do it a lot, you get nonsense, okay? So there are two dumb people out there. There are people who don't use, this is dumb, don't use this principle, okay? And you hear a lot of this in fake news and political discussion, okay? You can say something like, say, this government is bad because we have more people dying from epidemics than all the other government. Well, obviously, you're not controlling for the pandemics, right? That sort of thing. It's sort of like, life was much better when I was a kid. Well, there's a whole bunch of other things. It has not to do with you being just a kid. So that's stupid, right? That's saying, you don't use this principle. The other thing is to get carried away and say, well, if you move x3 just a little bit and you get increase, let's move x3 quite a lot. And that's completely nonsense. That's all nonsense. They're both nonsense. This is the nonsense of economists. This is the nonsense of internet trolls. Okay, so you have internet trolls that make this kind of fallacy in their reasoning, and then you have economists that makes good economists don't. By the way, I'm just being funny. Good economists knows the limitation of ceteris paribus thinking. They just alter a little bit. They don't go all the way. Okay, that's like saying, all else being equal, if you drink a bit more coffee, my life is better if I drink more water. Okay, I'm drinking 5 glasses now. If I drink 6 glasses, my life is better. Well, based on that, all else being equal, the more water I drink, the better. So I drink the whole swimming pool worth of water in a day and I die. Okay, that's basically what the fallacy comes down to. But in real life, people make this argument and they don't realize they're doing it. Okay, so this is dumb because of this. This is dumb because of this. Okay, so let me show you why it is dumb from a technical viewpoint. This is
before we continue, can I pause the video and record in again?
Sure.
Okay.
Sure.